Okay, so let me briefly go over the properties that we talked about yesterday. Those of you who weren't here yesterday, just try to keep up as much as you can, and then you'll have time at some point, whether it's in here or at home, that you can watch the video from yesterday, and hopefully that will clear up any confusion you might have. Okay, so we're working on solving equations that have logarithms in them, and these properties help us do that. So the product property, the way that we're going to use them, kind of ignore this part. The product property is if you have two logarithms being added together, as long as they have the same base, you can rewrite it as one logarithm using that same base, and then whatever is here where the 5 is and here where the 6 is, those things get multiplied. So the two logarithms being added together, you change to one logarithm, and instead of addition, you multiply. The quotient property is if you have two logarithms with the same base that are being subtracted, we rewrite it as one logarithm, the base stays the same, and we divide 5 divided by 6, or whatever number comes first divided by whatever number comes second. The power property says if you have a number out in front of a logarithm, you can move that number so that it becomes an exponent on this number. So the 5 gets moved to be an exponent on the 6. The reason we want to do that is because to use the other properties, you can't have numbers in front of the logarithms. So there'll be times where we have to move those numbers so that we can then use other properties. Really quickly, just so that you guys who weren't here yesterday know what I'm talking about. The property on the front just tells us that if we have two logarithms that are set equal to each other, as long as they have the same base, whatever is here where the x is has to equal whatever's here where the 8 is. In order for these logarithms to have the same value, x has to be equal to 8. And we use that property to help us solve for x in some problems. So we did 3 examples yesterday. I'm going to go ahead and start with, I'm going to call this example 4, just to save any confusion if we're talking about these examples later. So example 4 is log base 6 of x plus log base 6 of x minus 9 equals 2. Log base 6 of x plus log base 6 of x minus 9 equals 2. Okay, first thing that sticks out to me is we have two logarithms being added together. As long as they have the same base, which they do, they both have a base of 6, we can combine these logarithms into one. When we do that, the base stays the same, so it's still log base 6. But then we take x and x minus 9 and we multiply, so x times x minus 9. So we've used the product property to combine these two logarithms into one. Let's go ahead and do this multiplication by distributing the x. So we have log base 6 of x squared minus 9x equals 2. So now we've gotten to a place where we have something that doesn't look like anything that we did yesterday. Yesterday we had a logarithm equals a logarithm, and we were able to, as long as the bases were the same, we were basically able to leave the logarithms off. Now we have a logarithm equals a number. So we're not going to be solving it the same way. If you get to this point where you have a logarithm equals a number, it's similar to when we did things that look like this. You don't have to write this part, but if we had log base 2 of 8 equals x, in order to solve this, we would change to exponential form, say 2 to the x power equals 8. and then we would be able to solve for x. It's going to be the same thing here, even though it looks a little more complex. We can still do the same thing where we can use the loop trick to change this to exponential form. So start at the base, draw a counterclockwise loop around. And when we write this in exponential form, it is 6 squared equals x squared minus 9x. When you're working these and you get to a point where you no longer have any logarithms, that's when you start just doing the algebra that it takes to solve for x. So in this one, since we have an x squared and just an x to the first power, that should tell you that you're going to have to factor in order to solve, which we did this a couple times in the examples yesterday. In order to solve by factoring a quadratic, everything has to be on the same side of the equation, and you want your x squared term to be positive. It's positive right now, so I want to make sure it stays on this side. So I'm going to move this 6 squared to the other side. And I'm going to go ahead and just say, we know 6 squared is 36, right? So I'm going to subtract 36 from both sides. That cancels out on this side and leaves us with 0. Then we have x squared minus 9x minus 36. Once you have everything on the same side, we can factor into our 2 sets of parentheses. So we know that x goes at the front of both of those. Then we're looking for 2 numbers that multiply to be negative 36 and add to be negative 9. Okay, let's just make a list. This helps me sometimes if I don't know what numbers to use. I need factors of negative 36. The first factors of 36 that I think of are 6 and 6. But in order for them to multiply to be negative 36, one of these would have to be negative. If that's the case, negative 6 plus 6 is 0, not negative 9. So that pair of factors doesn't work. What are more factors of 36? 4 and 9. So if I use 4 and 9, I know one of them has to be negative. So let's try negative 4, positive 9. Those do multiply to be negative 36, but when you add them together, you get positive 5. We need it to be negative 9. Well, let's just try, let's say we still use 4 and 9, but now we make the 9 negative. That still doesn't add out to be negative 9. It adds to be negative 5. Those don't work. What other factors of 36? 3 and 12. Okay, one of them's going to have to be negative. Which one should it be? Okay, if the 3 is negative, yeah, negative 3 plus 12 is a positive 9. We need it to be negative 9. So yes, 3 and negative 12 should work.
And then it doesn't matter where you put those numbers in.
Correct. It doesn't matter. You could put plus 3 minus 12, or you could put minus 12 plus 3. It doesn't matter. I'll do minus 12 plus 3. After you get your factors, the next step in solving for x is to set each factor equal to 0 separately. So x minus 12 equals 0 and x plus 3 equals 0. Then we can solve each of these equations for x. So add 12 to both sides to get x equals 12. Subtract 3 from both sides to get x equals negative 3. So this is the step yesterday that I told you you could skip if you want to. Notice our answers that we got are the same numbers in our parentheses, just opposite signs. So you could skip straight from here to this step if you wanted to. So I have a factor of x minus 12, that means x equals positive 12. I have a factor of x plus 3, that means x equals negative 3. If you can remember that it's going to be the same numbers, just opposite signs, that's fine. I don't have to see this work in between. Okay, once we get our two answers, or any answers that you get when you're working these problems, you have to go back and check them. Because what we learned yesterday is inside of a logarithm, this number, wherever x is, and this number, x minus 9, those spots in a logarithm cannot be negative numbers. So because we're working with logarithms, we have to go back and check to see if these numbers create a problem for us. So let's first check x equals 12. So plug 12 in for x in our original problem. Log base 6 of 12 plus log base 6 of 12 minus 9 equals 2. So I can already pretty much tell that we're not going to have an issue having a negative in one of those spots, but let's go ahead and do that very simple math of 12 minus 9. So we get log base 6 of 12 plus log base 6 of 3 equals 2. So for those of you who weren't here yesterday, if you were to end up with a negative number in either of these spots, you could not use this x equals 12 as a solution. You would have to stop right there. Both of ours are positive though, so we don't have that problem. Okay, once you've made sure that there's no negatives, you can basically follow the same steps that we took when we were solving. So the first step we did was to combine these two logarithms into one. So log base 6 of 12 times 3. Then we changed this to exponential form. So we get 6 squared equals 12 times 3. Six squared is 36. 12 times 3 is 36, and 36 equals 36 is a true statement. So everything checked out. We didn't have any negatives where we're not allowed to have negatives in a logarithm. So x equals 12 is a solution. We circle it to show that we have checked it and we know it works. Okay, let's try x equals negative 3 as a solution. So plug that into the very first line of the problem, log base 6 of negative 3 plus log base 6 of negative 3 minus 9 equals 2. So automatically, I see a negative where we're not allowed to have a negative inside of a logarithm. So just to reiterate, if we're looking at log base 6 of negative 3, this logarithm is asking 6 to what power equals negative 3. There is no exponent that you can put on a positive number that will then give us a negative answer. And if you try to put log base 6 of negative 3 in your calculator, it gives you an error because it's going to be a non-real answer. So because we have a negative where we're not allowed to have a negative, we can cross out x equals negative 3. It is not a solution for this problem. As it turns out, this negative 3 minus 9 is also going to end up being negative, but it really doesn't matter. Even if one or the other is negative, that still stops us. Now, there is something I want to point out. Don't write this part, just take a look. If I were to keep going, And I said, okay, the next step we took was to combine these logarithms into one. -3 minus 9 is a -12. Well, then when I multiply -3 times -12, I get a positive 36. I no longer have a negative where I'm not supposed to have a negative. Okay, that's all fine and great, but we cannot do that. I'll explain a little bit of why. We had to use a property of logarithms in order to basically force this to become positive. If you have to use a property to change the sign of something to be able to keep going, we're not doing that. Now, if you think about on the front page, those of you who were here, in example 2, we were checking x equals -4 as a solution, and we had -4 squared, which then gave us a positive 16. But that happened because that's how the problem is written. It's written as x squared. We didn't have to use a property to force that to happen. It happened because that's how it's written in the problem, and that's fine. It's when we would have to use a property of logarithms in order to force this to become positive. That's what we don't want to do. Now, if this -3 had an exponent of 2 on it, and this over here turned out to be positive as well, then that's fine. But because we had to use a property to force it to become positive, that's a no-go. Any questions on this example? I know there's a lot of steps and it's long. We're going to do more. This isn't the only one. Okay. You'll need probably another sheet of paper. If you have notebook paper, grab a sheet. If you don't, I have some that you can have. Okay, this will be example 5. We've got 2 log base 7 of x equals log base 7 of 27 plus log base 7 of 3.
No. Miss Fulmer,
Yes.
do you have Ariel Garza?
Yes.
Could you ask her to come to the counselor's office, please?
Sure.
Thank you.
Yeah, go ahead. Good luck. Okay. So on the left side of the equal sign, we need to deal with this 2 that's in front of this logarithm. In order to use the other properties on down in this problem, you can't have a number in front of a logarithm. So the power property that we learned about yesterday says that we can rewrite this as log base 7 of x squared. So we basically just move this 2 so that it becomes an exponent on the x. That's what the power property allows us to do. On the right side of the equal sign, we have 2 logarithms with the same base that are being added together. We want to rewrite these as one logarithm. So when we do that, the base stays the same. So it's still log base 7, but then instead of adding, we multiply 27 times 3. Okay, this is where it's different from example 4. It's not a logarithm equals a number. It's a logarithm equals another logarithm, which is what we did yesterday. So because these 2 logarithms have the same base, we know that x squared has to be equal to 27 times 3. So we're going to set those equal to each other in order to solve for x. x squared equals, let's go ahead and do 27 times 3 is 81. So we do have an x squared term, but we don't have a term that's just x to the first power. So we don't have to get everything to one side and factor like we have on a few of these other examples. Instead, to solve for x, just take the square root of both sides. The square root and the squared cancel and leave us with x. And then what's the square root of 81? 9. Could it just be 9? What about x equals negative 9? Yeah. So we do want to include the positive and negative square root. If you do the square root of 81 in your calculator, it's probably only going to give you the positive answer. You just have to know in your head that, well, negative 9 times negative 9 is also 81. So negative 9 could be a answer as well. But we need to check both of these answers to see if they actually work as solutions. So we're going to go back to the very first line of the problem and plug in these values for x. So if we're trying x equals 9, we've got 2 log base 7 of 9 equals log base 7 of 27 plus log base 7 of 3. We don't have any negatives where we're not supposed to have negatives in a logarithm. So the way that we can check this is to just follow the same steps that we took when we were solving. So move the 2 so that it becomes an exponent on the 9. So we get log base 7 of 9 squared. Combine these two logarithms into one logarithm to get log base 7 of 27 times 3. Set 9 squared equal to 27 times 3. And 9 squared is 81. 27 times 3, also 81. So 81 equals 81 is a true statement. That means x equals 9 is a solution. It did work. So we circle it. Okay, let's try x equals negative 9 as a solution. So going back to the very first line of the problem, plugging in negative 9 for x. So immediately we notice there is a negative where there's not supposed to be a negative in a logarithm. This is why it's important to go back to the very first line of the problem, because if we were to go to the second line where we've already moved the 2 as an exponent, this might not be a problem because negative 9 squared will give us a positive 81. But because we have to use a property in order to force that to happen, negative 9 is not going to be a solution for us. If the 2 started as an exponent instead of being down in front of the logarithm, then we'd be okay. But because we would have to then use a property to force this to become positive, we're going to stop right there and say x equals negative 9 does not work. Questions on this one? Okay, I have 2 more examples. They are very similar to the 2 examples we just worked. So I'm going to write them out and let you work them on your own or with someone next to you, and then we'll talk about what the answers are together at the end of class. First one, log base 6 of x plus log base 6 of x plus 5 equals 2. This one is almost exactly like example 4. You can pretty well follow the same steps that we took in example 4. Number 7, 4 log base 2 of x minus log base 2 of 5 equals log base 2 of 125. This one's not exactly like any example that we've done so far. Just work on example 6 for now. We'll use the rest of class time for example 6, and we'll start with example 7 tomorrow. I don't think we'll have time to get them both done today. So work number 6 by yourself or with a partner, and we'll talk about the answer at the end of class. Don't worry about example 7. I didn't realize that it was not like one we'd already done.